All right. So in this example, what we're going to look at is this example is actually modeled by how the dinosaur died. The numbers that I took from. Okay. So now in the most believable hypothesis that we have at this point, the dinosaur became extinct very suddenly. Like over the course of only a few million years, you have like dinosaur dominating the earth to like no dinosaurs at all, right? Now, the most believable hypothesis, I mean, I call it a hypothesis because unless we have a time machine to go back to the past to actually see it, I mean, it could only be a hypothesis, right? I mean, no one actually know. But according to our most believable hypothesis and also some facts that we we do have actually facts that are based on, that can support the idea, is that the dinosaur was killed because a very, very big asteroid hit us. And when an asteroid hit us, this one particularly hit the ocean and it evaporate a huge part of the ocean. And then all the steam and dust underwater and dirt underwater end up just exploding to the sky and covers the entire Earth. Now, without the sun, Earth's average temperature is actually -50 or 100 degrees Celsius. I mean, the average temperature on Earth right now, if you count like every single part of the Earth, including, the Sahara, which is like in the 50s, or including the North Pole, South Pole, which is like negative something. The average temperature on Earth right now, because the sun is here, is around like 15, I think it's like 12 to 15 degrees Celsius on average, okay, everywhere on Earth. But that explosion, right, that asteroid hit, basically created a very, very long-lasting cloudy sky. And by long-lasting, I mean like thousands of years. So the Earth was entirely blocked out from the sun for thousands and thousands of years. So what happened? The surface temperature dropped drastically because there's no sunlight coming through anymore. The explosion from the asteroid hit basically destroyed everything. Now, so when the sun is gone, then plants that relies on the sun, which photosynthesis, right? That's how plants get their food, photosynthesis and water. Those plants die. Then animal, which are herbivore that eats those plants, they die. Then herbivore, which most of the dinosaurs are, that eats meat, well, they run out of food too. And in those situations, the bigger you are, actually, the worse it becomes. Because when you think about it, the bigger you are, the more you have to eat, right? And when food is scarce, the more you have to eat. That means the more likely that your species are going to go extinct. So dinosaurs were all gone. Within a couple hundred, well, within like a few million years, we went from like dinosaur everywhere to like zero dinosaurs almost. Our ancestor, yes, humans' ancestor. I mean, when we say our, I mean mammals, right? Our ancestor at that point is this like giant mouse thing that really looks like a mouse, but it's like gigantic. Imagine like a car-sized mouse. That's kind of our ancestor at that point. They survive. They're small enough and they can hibernate. They can hide. So crocodiles survived. Turtles survived. But not all the animals. Like most of the animals, 99.9% of the animals on Earth were all extinct at that point, right? So the astronaut I picked for this question is actually modeled after that one. According to some research, the impact crater of that asteroid hit is still visible on Earth. You do have to go to Google Map if you want to see it, though. It's off Mexican Gulf. So let me see if my geography is good enough to actually point it out. But I will point out for you. They have found the crater. I mean, hypothesis, okay, again. So let me, I'll assume now. We have to go to Mexico. Okay, so Canada, okay. US, this, okay, come on. This, that, here, this. Can you see that? That was the impact crater that killed the dinosaur. I mean, it was a piece of land, but then, the asteroid hit, and then now it's an ocean. Right? I mean, of course, this happens 63 point, I don't remember the last digit, 63 million years ago, right? A long, long time ago. But people have been doing research, and then this is now our most believable hypothesis. The asteroid hit exactly over there, and then basically created a mini ice age, like instantly. I mean, Earth goes under its own ice sheet from time to time, but this one is induced by an asteroid hit. And every time an ice sheet happens, most of the animals just die off, right? So now, so what I want to find out is how much energy is actually released by such an explosion. Okay, so when asteroid or stars or planet hit each other, the calculation is not actually that difficult. Okay, so you start with a planet, right? So let's start with us, right? Earth. Okay, now imagine that dinosaur is still alive. I love dinosaur, so I'm going to draw one. That's not a dinosaur. There you go. Dinosaur. Okay, dinosaur. So imagine the dinosaur is still there. And then we have this asteroid from really, really, really far away. Okay, this asteroid from really, really far away coming toward us. Now, let's assume that it's so far away at the beginning that we consider it to be starting at rest. Now, technically, we don't know where the asteroid came from. So maybe it started at rest, maybe we didn't. But for the sake of our calculation, let's imagine that the asteroid started at rest. Right? So V initial is 0. Okay, so if V initial is 0, that can only mean one thing. Kinetic energy must be 0 to begin with. Now, again, we are assuming things in here, but not unreasonable. So no kinetic energy at the beginning. Now, at that point, though, however, you do have potential energy, and it's called gravitational potential energy, which you can calculate. But remember, we're assuming that the asteroid started really, 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 really far away. Now, according to, I know it's last week when we talked about this. Okay, so let's look at the potential energy equation. Remember, the potential energy equation that we use is treating potential energy as a deficit. So we are all in debt to the Earth gravitational energy, potential energy. So now, if you start from really, really, really far away, your potential energy at that point is actually 0. You get more and more negative as you get closer and closer to Earth. But if you go really, really far away, your potential energy is 0. If you go far away enough, you're no longer bound by the Earth. That means you have paid off all your debt and you can actually escape, right? It's almost like just like a debt collector, right? If you owe them money, you cannot escape. You pay them more, you can escape. So if you're really, really far away from the debt collector, that means you have paid off all your debt already. So in this situation, we're going to assume that the asteroid that we have started really, 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 really far away. That means it started with a potential energy of 0. Okay, now, and then here's the impact, right? So here's the impact. So impact right here, and then, fire, explosion. Okay, like that. So then the impact. Okay, so now at the impact, what happened? So just before you hit the Earth, you are going really fast. You have been accelerating, getting attracted by Earth's gravity. So you speed up as you approaches the Earth, right? So you go really fast. Now, actually, what happened is you go faster and faster and faster and faster until the moment you hit the Earth, you're at the fastest speed that you ever get. And then suddenly, you hit like a ginormous object called the Earth, which means all of your speed is now you suddenly stop, right? So it's like you driving really fast and you hit a wall, you stop all of a sudden. When you stop, all of the kinetic energy that you had before is gone. But remember, energy cannot just be gone. Energy has to be transformed to something else. So for example, when you drive and you hit the wall, the energy of the kinetic energy just before you hit the wall is not gone. It's converted into heat and energy that bend your car and do all the, and sound and heat and light sometimes. So this is exactly the same idea. The energy, the kinetic energy that you had just before you hit is completely absorbed by the Earth and the asteroid, and it turned into heat, okay? So basically, all of this kinetic energy just before you hit the ground, so you have like a lot of kinetic energy, which can be calculated by 1/2 mv squared. We don't even care about that part. I just wanted to know that all of these energies just turn into heat when you hit the Earth. And the heat, that's the explosion, right? The heat, light, sound, that's the explosion. And that is what killed, well, the dinosaur in this case. Okay, so the potential energy at that point is something. We don't know what it is. Okay, so now according to conservation of energy, the total energy in this two story must be exactly the same since no other force is disturbing it. So if I count the total energy in here, it should be the same before and after, right? So that's conservation of energy, and it's still true in space, of course. So the energy from the astronaut is not gone. It's just turned into heat, which heat up the Earth and heat up the asteroid. The asteroid completely melt, and then the explosion creates this like perpetual cloud in the sky for like thousands of years, and then all the dinosaurs die, all the plants die, like that, right? So now, so we can still use something like this. So the amount of kinetic energy that you gain, right? So the amount of kinetic energy you gain plus the amount of potential energy that you lose must be the same, right? Like the amount of kinetic energy that you pick up must be equal to the amount of potential energy that you lost. So in this case, if I rearrange the equation just a tiny bit, then I have kinetic energy gain is equal to negative of potential energy loss. And if I have my kinetic energy gain as the equation, right? Now, so all of these are going to into heat. Now, the question is asking us how much heat does it actually release? So we can just answer that, right? So how much heat is released is the negative of the change in potential energy. Okay, how do you do change in potential energy? Final minus initial, right? But remember, last day we actually combined the equation a little bit, and we had like a slightly nicer looking version so that we don't have to do final potential minus initial potential and then have like double negative, 3 negative signs somewhere. We had this equation last day for change in potential energy. So if you use this instead of using the 2 giant equation over here, we'll save ourselves some time because we don't have to plug in G twice or big M small m. So we're going to use that. Whatever time we could save, right? Now, okay, so not too bad. So this is easy to do. So you're basically just doing. Oh, actually, you know what? I don't think we even have to do that because I think the initial potential is 0. So that is convenient. You know what? I'm just going to do final minus initial. We don't even have to involve that equation because initial potential energy is 0. Okay. So now we have a answer. How much energy is going to be released? Is just the negative of the potential energy that you have when you're on the surface of the Earth, which is G, big M, small m, over R. Okay, what R? Now, remember, this is your final location. So that means from here to here, your final location. But isn't your final location just the radius of the Earth? Because that's the surface that you're hitting, right? So your final location is just the radius of the Earth. Because at the end, when you hit something, you're hitting the radius of it. You're hitting the surface, right? So from the surface to the middle of that planet is the radius of the Earth. So all we have to do is put radius of the Earth in there. Now, actually calculate how much we will get. Mass of the first object is Earth. So 5.98 times 10 to the 24 kilogram. And then the asteroid is 2.35 times 10 to the 16. So 2.35 times 10 to the 16. Okay. And then dividing by the radius of the Earth, 6.37. Is it 37 or 38? I think it changes. 38 times 10 to the 6. And then that's it. Okay. Now, of course, there are going to be some round off, but I am going to have my answers here soon. What you can hear, approximately for me, is about 1.5 times 10 to the 24 joules. Now, how much energy is that? The first atomic bomb, the one that's dropped in Hiroshima, right, to end the Second World War, partially, released approximately the first atomic bomb ever dropped, releases approximately 6.3 times 10 to the 13 joules of energy. Now, how much is the difference between 10 to the 13 and 10 to the 24? How much? 11 more zeros. So 100 billion times. 9 0 is a billion, right? So 11, so 10 0 is 10 billion. 11 0 is 100 billion. So, I mean, yeah, the number is not exactly the same, so we'll cut it in half. Let's say 50 billion times. So this asteroid hitting the Earth is equivalent to dropping 50 billion atomic bomb. And you know what the first atomic bomb did? It levels a city. So now we're doing what? So this asteroid is 50 billion of that. Okay. So no surprise that, 99% of the life on Earth was extinguished, right? So like they are all gone. Right? This is very, very big impact. Okay. I mean, you have to have something that big though. I mean, this asteroid is very big. The mass is, in the trillions of kilogram and hitting us from very, very far away. Okay. So what happened if I tell you that, let's say we have an asteroid like that coming. We only have a few days to escape. Then everyone will be in panic, right? Everyone is in panic. Well, luckily you know physics. So let's calculate the escape velocity. So the escape velocity is the speed that you need to fly or travel at in order to completely escape from the planet that you're on. Now, we are on Earth right now, so we'll calculate the escape velocity from Earth, surface of the Earth. But, one day if you're on the moon and you want to escape from the moon, the calculation have to be done again, and it will be a different number. On Mars, different number. On Jupiter, different number. If you want to escape from something else, the number will be different. But since we are all on Earth and we are all going to run away from that giant asteroid over there, let's escape on Earth. Okay, so escape velocity. Now, to understand this, right? To understand this, we go back to the notes, go back to this page. Remember, potential energy is a debt. That's how much you owe the Earth right now. Earth is the debt collector. We owe the Earth money. In order to escape from the Earth, we have to pay off every single cent that we own. Now, just like, a debt collector or a bank, when you owe them money, they will charge you interest, right? So if you don't pay up everything, eventually, so let's say you owe the bank $1 million, but you only pay them 500,000. So you still owe them 500,000, right? So in a few years, you will go back to owing them $1 million. Why? Because the interest of what you owe what the remaining part of your debt is going to grow again and make you owe more and more in the future. Another way to think about it is, so that's the reason why you had to pay off everything in one setting. Now, another way I can think about this, right, is imagine that this potential energy graph is physically actually a well or like a hill, and we're in the bottom of that well. Imagine that this is you and you're kicking a football. This is your football, right? Now think about it. If you kick the football with enough with a little bit of kinetic energy, then it will go up to this point, and then what? And it roll back down. That's what happened on anything that you throw up in the sky on Earth. It eventually come back down because you didn't give it enough kinetic energy to escape in one setting. So eventually Earth will pull it back down. But what if you kick it so hard that it can actually go? Then it won't come back, right? So that's what we are aiming for. We have to give the object enough kinetic energy, which is positive energy, so that you can pay off the entire deficit on you to the Earth. You pay off every single joules of energy that you owe the Earth, then you can escape from it. The more, the merrier. You can actually have more, right? But you have to have at least enough to pay off your potential energy debt. Okay, so this is what we're going with. Supply the object. In order to completely break free from the Earth, we need to supply it with enough kinetic energy. So kinetic energy. Okay, so kinetic energy. So that to match is potential energy. So potential energy. So we are going to pay our potential energy deficit with kinetic energy that we can generate. Okay, so supply it with enough kinetic energy to match its potential energy at infinity. Okay, now, very simple idea. So what does that mean? That means I want my kinetic energy, EK, to equal to my potential energy deficit, EP. Or, technically, okay. Technically is I want the total energy to be 0, so that if I move the equations around, I will have my kinetic energy equal to negative of my potential energy. Now, that in the equation will look something like this. 1/2 mv squared, right? That is your kinetic energy. and you make it equal to the potential energy without the negative, because we have a negative in front of something that has a negative, so it cancels out. So Gm1 over R is our potential energy. Now, you notice that the mass of the person escaping, which is small m, is actually gone. That is insane. Okay, we have a planet, big M, right? We have a thing that want to escape. Now, what would be the thing that we want to, an apple. We want to throw this apple to space. So the apple has small m. So how fast do we have to kick the apple so that it can escape from the Earth and never come back? It turns out the first thing we have to do to the equation is kill off the mass of the apple. Okay, well, but okay, let's keep going. Let's keep going, right? Okay, mass of the apple is gone. The mass of the Earth is still there. Okay, now multiply both sides by 2, take a square root. Ladies and gentlemen, we have escape velocity. Okay, so this is the escape velocity equation. Now, one thing that's really cool about this equation is the fact that whatever escape, for example, in this case, it could be the apple, doesn't actually matter. This escape velocity is extremely fair to everyone who is on the surface of the Earth. For example, an apple will lead that speed. A human would also lead the same speed. Or if you want a dinosaur to escape, you also give the dinosaur the same speed. Or a rocket. If you want a rocket to leave the Earth and actually travel to another planet, you also lead the rocket to have the same speed. Therefore, that means we only have to calculate this speed one time, and that's it for every single object on Earth, on the surface. They lead that speed to escape. That also means I cannot ask you the same question again on the test or on the assignment, because it will be exactly the same answer. So on the test, on the assignment, expect to do other planets, not Earth, right? I mean, we are doing Earth right now, and it will be done in a few seconds. And once Earth number is done, then that's it, right? It's going to be that number. I might ask you to, like, if you can recognize it. It's a number that some people just recognize. It's kind of a cool thing. Okay, so now what we need is mass of the Earth, and where are we escaping from? We are escaping from the surface of the Earth. Okay, surface of the Earth. So the distance is the radius of the Earth in this case. Okay, so we can escape from places that are further away. Then we don't have to be going as fast. But let's try to escape from, so this is kind of like your initial distance from the center. But if you're standing on the surface, then your initial distance from the center is the radius of the planet. So that will be cool. So 2g, I'm not writing g anymore. Mass of the Earth, I'll write 5.98 times 10 to the 24 kilogram. And then we are standing on the surface with this rock, so apple. So 6.38 times 10 to the 6 meter. Okay, and then just giant square roots on the number at the end. Now, when you put all of these in the calculator, you're going to get a result that is surprisingly not big. Right? Surprisingly not a big number. So you're going to get 1.1 times 10 to the 4 meter per second. 11, so approximately, right? 11,000, right? 11,000 meter per second. So how fast is that, right? I mean, okay, so fine. Let's do km per hour because, well, let's do km per second. Let's do km per second. 11 kilometer per second. Now, I know km per second is a weird unit, but it's kind of nice to look at. 11 kilometer per second. Okay, so let's put that in perspective. From here to Surrey is 20 kilometer. That means the speed is from here to Surrey in 2 seconds. Or from here to Vancouver in 1 second, which is about 10K, right? From here to downtown Vancouver is about 10K. So this is how fast you need to kick something. So for example, let's say I really would like to send, let's say, Jordan to space so that he can travel, right? He can become a space traveler. Then how fast do I have to launch a Jordan? It will be 11 km per second. Okay, so if I can, have a giant slingshot, right? Like gigantic slingshot that can actually, shoot something at that speed without air resistance, of course, then a Jordan will not come back. Like you can be a satellite forever, right? You can actually orbit the Earth and be a satellite. Now, that speed is going to, does the mass of the rock matter? Nope. So that's what we were talking about, right? So the mass of the object itself actually doesn't matter, which is a very fun fact, right? The mass of the object itself doesn't matter. So it's sending either, like you can send whatever you want, and the speed is approximately 11 km per second for everything. So imagine how you would do it for Mars, Jupiter, other planet. The only thing that will change is the mass of the planet that you're escaping from and the distance that you're escaping from. So the radius of the other planets, right? You know, have you ever heard of someone saying, you know, even in movies, that if you get caught in a black hole, you cannot escape? You know why you cannot escape? Because the speed limit of the universe is the speed of light, which you learn in one of our chapter in about a week or so. The speed limit of the universe is speed of light, which is about speed of light, 3 times 10 to the 8 meter per second. Now, it turns out that the escape velocity from a black hole is faster than that. You need to be faster than light to escape, but nothing can be faster than light. Therefore, no one can escape a black hole. So if you calculate the escape velocity from inside the event horizon of a black hole, that number is faster than this value. And nothing in our universe can travel faster than that value. And only one thing can travel at that value, which is light. Nothing else can do it. We will talk about speed of light and its limits and everything in our special relativity from Albert Einstein unit coming up. But that's how they actually find out you cannot escape, because the velocity is faster than what the fastest one we are allowed to do. Okay, so